about, say, why don't you talk about the latest in astrophysics? What's the latest? What's going on that's really out there? And so, I'd love to do that. The only problem is that it turns out the universe is really, really big. And so when you ask me, what's out there, what's really interesting, you first have to understand just how big the universe is. So there's no way I can tell you all of the interesting things going on out there, all the latest results. There's just too much. There's new research breakthroughs coming out every day, but I thought I should at least start by just conveying to you quite how large the universe really is. So you're probably familiar with this planet here. This is the Earth. And of course, the Earth is part of a solar system, and the solar system is depicted here. It's not very good, but you can see the little red thing. That's Earth. The little red thing is always is where the previous object is, and you can see the sun's at the center, a star surrounded by planets, and there's asteroids and all sorts of fun things in there. But of course, the solar system is part of a much larger interstellar neighborhood. So this is the interstellar neighborhood, the closest stars to the solar system. And the solar system really is just, on this scale, is just a dot. And that's red over there. It says solar system red, but the solar system on this scale is really just a tiny dot. Those are our very closest neighbors, and they make up the neighborhood just around where we are in our galaxy. And we're in a galaxy called the Milky Way galaxy, and here it is. And so now this whole solar neighborhood, where the solar system is just a dot, now that whole neighborhood is now just a little dot over here. That's where we are in the galaxy. And I just have to stop and say, you might think, I've told you it's the Milky Way galaxy, but really you should know that's not the Milky Way galaxy. And you should know that because it's impossible to take a picture of the outside of your house if you're standing inside the house. Just, you cannot do that. So this is what we think the Milky Way galaxy looks like on the basis of observations and also of studying the night sky and seeing all the other galaxies out there. Really, if you want to see the Milky Way, this is a beautiful image. The Milky Way, so these are obviously all stars, and the Milky Way galaxy, the disk, we're right in the disk of the galaxy, so it's hard to see to the center, and there's also, annoyingly, there's a lot of dust in the way, so if you can ever see the sky, and it's not impossible to see this with your naked eye, a lot of the light from the central regions of the galaxy is hidden by dust. But in any case, just coming back to the bigger picture, right, so not the Milky Way galaxy. That entire galaxy, of course, is part of what we call the local galactic group, and now the Milky Way is just a little dot in the local group. These are all now galaxies. So the Milky Way is actually one of the bigger members of the local galactic group. Another one is the Andromeda galaxy. So this is the local galactic group. And this is like our nearest neighbors in terms of galaxies. That's just the nearest neighborhood, the closest galaxies to us. And this whole local galactic group is part of what we call the Virgo supercluster of galaxies. So now this entire local group of galaxies is just a dot in the Virgo supercluster, which itself is part of a whole web of superclusters. Of each of these is a cluster of galaxies. And this entire local supercluster of clusters of galaxies is part of is a dot, where each of the dots that you see in this now looking at the universe on the largest scale possible, these are all superclusters of galaxies. So when you say, what's new in the universe, it's hard, and you have to understand astrophysics. So people who study the Earth, they're usually called geologists or atmospheric scientists. People who study the solar system are typically planetary scientists. So astronomy really starts over here. So what we call astronomy or astrophysics is from here on. And if you ask, okay, where do I do my work? I'm almost exclusively inside the galaxy. So just so you understand that. And I'm going to talk about my work a little bit later. But first, I think it's important to understand how big the universe is. But what makes it even harder to understand all about the universe is the fact that it's getting bigger. So the universe is expanding. This is, and what I mean by expanding is that the separation between galaxies is increasing. Space itself is expanding. And this might sound, might sound crazy, might sound like the first of the new astrophysics that I'm describing to you, but this is actually in astrophysics, we've known this for many, many decades. In fact, the fact that the universe is expanding was discovered by the famous astronomer Edwin Hubble, after whom the famous telescope was named, back in 1929. So the expansion of the universe has been known, and here he is pictured with a pipe. He's almost always pictured with a pipe. I can't explain that, that's just how it is if you look, Google him. And what he did is he observed with optical telescopes distant galaxies, and he made an astonishing discovery. He found that every galaxy in the sky is moving away from us. No matter which direction you look, all galaxies are receding away from us. And not only that, he also showed that the speed with which they're moving away from us gets larger the further the galaxy is away. So the most distant galaxies are moving away from us really fast compared to the closest galaxies. But irrespective, everything is moving away. And then given the fact that it's clear where we are in the galaxy, there's nothing special about our location, the explanation is that space itself is expanding. And when I say all this, it must sound crazy. And you might say, how do you know space? How do you know this? Do you look and then you look the next day and everything's a little further away? Or are things getting smaller on the sky? So no, it does not come from imaging the sky, because even though things are moving away pretty fast, it would take millions of years to be able to detect that galaxy over there is a little bit smaller after a million. So you need millions of years to see that effect. I just thought I'd show you, this is a real image of the sky taken by the Hubble Space Telescope. And this is called the Hubble Ultra Deep Field. It's an image of a blank part of the sky. And what I mean by blank is that it's a part of the sky where there are no stars, local stars, no stars in our own galaxy. So all those annoying foreground Milky Way stars, at least annoying to some people, I like them, but to the extragalactic people, they've looked in a blank part of the sky for a very, very long time with the Hubble, and every dot that you see here is a galaxy. These galaxies, but if the Hubble goes back tomorrow or in 10 years or in 1,000 years, it's the same part of the sky is going to look the same, even though the universe is expanding. So the question is, how do we actually know that the universe is expanding? And that's what I'm hoping to explain. But first, you need to know a little bit about light. So the way we answer these kind of questions, the way we study them in astronomy is almost exclusively through light. That is the workhorse. Telescopes, we collect light, we look at it, we analyze it, and not everything is imaging. So it's not just about taking pictures. So I'm going to now explain to you some things you need to know about light to understand how we know that the universe is expanding. So the first thing that you need to know is that white light is actually made up of the colors of the rainbow. So if you take a prism, I hope most of you played with a prism, and you shine some white light through it, it's going to disperse it into all the different colors of the rainbow. And here's a diagram. We call all those colors a spectrum. And of course, you're familiar with this. Even if you haven't played with a prism, if you've ever seen a rainbow in the sky, the rainbow is caused by little droplets of water in the air that are acting like prisms for the sunlight coming through. So basically, you could think of the water droplets in the sky as sort of being prisms that spread out the white light from the sun, from the sun. Now, if you could take a closer look at sunlight and spread it out even more, and have really bright sunlight, so you're focusing it with some telescope or some magnifying glass, and spread it out a lot, you would notice something interesting about it, and that is that it's not a perfect continuous spectrum. There's actually these thin black lines there. I hope everybody can see that. There's thin black lines. And if you could spread this out, take the same solar spectrum, and spread it out even more, and spread it out so it's not just across the screen, but it goes all the way down the hall and to the other side, to the entrance, and spread it out so much. And I can't show it to you that way, so I'm going to do that, but then wrap it around the screen. So let me show you what I mean. This is an even closer look at sunlight. And you can see I've wrapped the blue around, so that really you should think of this as all spread out, but I've had to fit it on a screen, so it's been wrapped. You see very clearly these black lines, and it doesn't look random, or it shouldn't look random. It almost looks like a code. Now before you think I'm going loopy on you, it is a code, but it's a natural code, a naturally occurring code that is telling us the constituents of the sun. The lines in the solar spectrum are telling you what the sun is made of. Let me explain what I mean by that. So if you remember from high school, the periodic table of the elements, all the different atoms that exist on Earth, the different atoms, hydrogen, helium, oxygen, these are all different types of atoms. It turns out that each atom produces its own unique signature of light. When you take some gas of it and you and you heat it up really hot, make it really hot. So for example, if I could take some argon gas, I've just circled one random element, argon gas, and we're about to do this. So I have some gas I brought, and I'm going to zap it with high voltage. What you're going to see is a little tube. If I have a vertical tube, it's now a thin tube of argon gas. It has a very clear, what we call spectrum, which consists of individual lines of light of a very specific color. It's a little signature that it's argon. Argon always has those same colors. And then if I take a different one, let's say I take helium, and in fact I brought helium, that's one of the ones I brought. It has a totally different spectrum. And you can recognize the elements by this. You do it in the laboratory, you can recognize them. So here's a few different types. I brought some, these are spectra for silicon, for sulfur, for iron. And let me just show you so you can see it with your own eyes. I'm going to ask you now to put on your glasses. And once you have them all on, we're going to take a picture because you all look so great that way. We have to record the event. And then we're going to turn down the lights. So what I have here is a gas discharge tube. I brought this from the physics lab at McGill. And inside I've put a thin tube of hydrogen gas. Hydrogen turns out to be the most abundant element in stars. That stars are almost all made up of hydrogen. I'm going to turn on the voltage. Try not to zap myself. There we go. Now if you look, now what you have here are glasses. These are not 3D glasses. These are prism glasses. So the film in there is acting like a prism, but spreading the spectrum out in 3 different directions. One horizontal, one vertical, one diagonal, and that's just because it looks cool that way. But just choose one direction, choose the horizontal one, for example. What you can see is this hydrogen gas has a very prominent red line, and then also a prominent blue line. That's why together it all looks a little purple. But that is the signature of hydrogen gas. And now what I'm going to do is I'm going to swap it, and you're going to see helium gas too. Hold on. It's very important that I turn off the voltage before doing this. Okay, putting in the helium. Okay. And you see now helium has a very different spectrum. The spectrum, you see very prominent orange line and also green, some red, but it is a different spectral signature. And each atom, I have, over there are tubes, I have argon, krypton, a whole bunch of different ones. Each one looks a little bit different. So I hope everybody was able to see that. I'm going to turn it off now and ask the light to come back on. And the point is, we have collected millions of spectra of stars in the galaxy. So for every, there's the Milky Way. Astronomers have learned about stars by measuring spectra. And what we know, because we can measure it in a laboratory on Earth, is that there's the stars are made of the same elements, the same atoms that we have here. There's nothing special in the stars. It's all mainly hydrogen, some helium. Certain stars like to produce more sodium. So it's very chemically peculiar stars. But we've never seen anything that's not recognizable from a laboratory on Earth. I think that's pretty amazing, actually. That's telling you can really understand astronomy on a physical level because we recognize the same kind of matter. And you might wonder, why does it make those specific? Why does hydrogen make those lines? And that's all very well understood. It's the realm of atomic physics. It has to do with electrons and where they orbit around nuclei, but never mind, I don't want to get into that. The point is, it's all very well understood physics, and every star that has ever been studied is recognizable in terms of elements that we know on Earth. And not only that, every galaxy, these are now all galaxies. Remember, galaxies are just collections of stars. Every galaxy has a spectrum that is the sum of all of the stars in there. So mainly hydrogen, helium, it's the sum of billions of stars, but it has its own spectrum. So you can measure the spectra of galaxies as well. Now I said I would explain how we know the universe is expanding. So now I've given you the brief light tutorial that you need in order to understand this. So something funny happens to light, and really to any wave. Light is a wave. When the light source is moving toward you or away from you. So if you have a spectrum, and let's say this is the regular spectrum of some element, I don't know what, that is sitting in a little gas discharge tube in front of you. If you take that tube and you send it careening really fast away from you, the spectrum's going to look a little bit different in that every line will have shifted a little bit redward toward the red side. So this line moves a little bit more redward, every line by the same amount. And by an amount that depends on how fast it's moving away from you. And in the same way, if somebody threw a light source at you, that would be bad, but let's say they did, if in that brief moment before it smacks you and you can measure its spectrum, you would see that the lines are blue shifted. So all the lines are a little bit shifted blueward. And this is a very well-known phenomenon called the Doppler shift, and it works for any kind of wave. It's also called the train whistle effect. You could think about it as if you have a car moving in this direction, the driver sounds the horn, and that's, of course, sound waves, not light waves, sound waves. The driver who's moving with the car hears a certain pitch of horn, honk, but somebody, observer over here who's standing behind the car will hear honk, a different pitch, because the wavelength's a little bit different. And an observer over here will hear a little higher pitch, a shorter wavelength, because the car's moving in that direction. And of course, the effect is largest when you're right along the line in which the car is moving, but that's not wise for observer 2, so I don't recommend observer 2 do that. But the point is that you can hear, when a car moves by you really fast, you hear eeeew as it's moving away from you. And of course, this is how police detect your speeding, because they bounce radar waves off you, and that's for radio light, and can measure the wavelength shift. And so the idea is that if you have a galaxy, you're watching it from Earth, and if it's fixed with respect to Earth, so it's not receding and not approaching, then the spectrum that you see will have the familiar lines that you're used to for hydrogen typically. Whereas if the galaxy is moving away, that line will be redshifted. The line that you see will be a little bit redward where it should be. And by an amount that's telling you exactly, according to a formula that I could derive for you if you came to my Physics 214 class at McGill University, the line is a little bit shifted depending on how fast it's moving away from you. And similarly, if the galaxy were moving toward Earth, you'd see that line a little bit blue shifted by amount that depends how fast it's moving towards you. And so this is what Hubble did. Hubble went out and measured spectra of, well, first he started with just a few dozen galaxies, and he plotted the redshift. First of all, he noticed they're all redshifted. Nothing was blue shifted. That was a shock. You might imagine if it's just a regular universe, some galaxies are just moving around. Some should be coming towards you, some should be moving away. But no, they're all moving away. They're all redshifted. And he plotted the amount of redshift versus distance. This is the only real plot I'm going to show you. It's from 1929. This is a reproduction of the original plot. He plotted the redshift versus the distance to the galaxy, and he noticed a correlation, which doesn't look very good, although I think with doctors here, for medical research, that probably looks really great. But I'll show you a modern Hubble plot, and you see the huge, very obvious correlation. The greater the distance, the greater the velocity with which the galaxies are moving away from us. And how can one interpret this? So the interpretation that then has been checked in many different ways that I don't have time to get into, you could think of it as an analogy with raisin bread. So if you bake a raisin bread and you have a bunch of raisins, you picture yourself sitting on some raisin, and of course the entire bread is expanding, and never mind the crust, ignore the curvy edges because that's just confusing. If you imagine a raisin over here, if the whole bread is expanding, then let's say it doubles in size in a minute. Then the separation between closer raisins, it doubles in a minute. So so it's moving away at this distance per minute. Whereas a more distant raisin, if that distance doubles in that amount of time, it's moving away even faster. And so the speed, so if the whole space is growing, it means the speed any raisin is moving away from another is proportional to their separation. So now, it's like I said, this is known since the 1930s. And what's new, so here comes new point number one. What's new in the world? Seymour wanted me to tell you, so I'm going to tell you, it's even worse. It's even worse. The universe is not just expanding. What has been known, what was awarded the 2011 Nobel Prize, is that expansion is accelerating. So the universe, yes, it is expanding, but it's expanding ever faster and faster. And you could, these are the three gentlemen that won the Nobel Prize: Adam Rees, Saul Perlmutter, and Brian Schmidt. And I'll just show you, there's Brian at McGill, at our little room at McGill. He's recording a podcast with some of my students. And if you want to hear the McGill Brian Schmidt podcast, all of our visiting scientists do podcasts. You can go online and Google that and hear him. He's a great speaker. He's a really nice guy too. But in any case, so the idea is that space isn't just expanding, that expansion's accelerating. And you can say, well, like, why? And the answer is, we don't know. So this is a mystery. It was a shock when it was discovered. People did not believe it, but the data are so, I don't have time to explain the data, but if I had 10 extra minutes, I could. But it's a big mystery. And here it was on the cover of Science magazine, The Accelerating Universe, with a picture of Einstein, curiously with a pipe. It's a running theme somehow. And you might say, what does Einstein have to do with this? I thought it was Hubble. And yes, it was Hubble who did the observations, but Einstein was a theorist at the time and played a very interesting role in understanding the expansion of the universe. And specifically, he made a huge mistake about it. So we all think of Einstein as a major genius, which of course he was. So much unbelievable science from a man, astonishing intellect, unparalleled, but he made a mistake. There's Albert Einstein in a playful moment. And that's John Malcolm. I found that on the web, and I just could not resist showing it to you, even though it's really irrelevant to my talk. But that's John Malcolm being Albert Einstein. I thought that was really cool. So why? I don't know. In any case, so Einstein in the universe. Until 1931, Einstein was convinced on purely philosophical, theoretical ground that the universe was static. And he argued this passionately when it was, what I mean by static, certainly not expanding. When he looked out in the sky, it looked pretty fixed to him. And this was what he believed. And when it was suggested to him, well, actually the observations are suggesting, Albert, that the universe is expanding, he said to admit even the possibility seems senseless. He did not believe this at all. But then when Hubble published his data and it was being discussed at conferences, and there were other signs as well that this was unavoidable, Einstein referred to his belief in a static universe as his biggest blunder. And indeed, it was definitely one of his biggest blunders. And if you want to read more about that, there's a really nice article about Einstein's conversion from the static to expanding universe. But Einstein actually provides a nice segue for me to tell you a little bit about my research, which is different. So I study pulsars, Morty mentioned, pulsars and neutron stars. So what is a pulsar and what is a neutron star? So a pulsar is a type of neutron star. That's the first thing you have to know. And so this is what should be in your mind. So you think of a star as the sun, a regular old star. Those are lots of stars like that. The sun's kind of a boring star. It's always on. The kind of stars that I study are very different. They pulsate, or rather, they're like little lighthouses in the sky, so that they spin about an axis and produce beams of light that come out at some different angle. And this is obviously a cartoon, and we never actually make this kind of picture. As I'm going to explain, these objects are so tiny on the sky that you cannot ever see this. All that we ever measure is the intensity of the light. So when one flashes at you, you see that and it repeats. So we record data very rapidly at telescopes using computers and study how these pulses come in. So this kind of star, it's not like the regular, the sun doesn't do this, obviously. It's a neutron star, and these are very special kinds of stars. So let me tell you a little bit about neutron stars. So for starters, they are pretty massive. So they have mass of about 1.4 times the mass of the sun. And that's not a very intuitive number for most people. So perhaps this will help you. It's about 500,000 Earths. I don't know if that's helpful to you or not, but if you took 500,000 planet Earths, that would be the amount of matter that's in one neutron star. But what's amazing about neutron stars is that all that matter is crushed into a sphere that has a radius of only about 10 kilometers. So, huge amount of matter. 500,000 planet Earths crushed into something that's smaller than the city. And this is what would happen. This is like a picture of a neutron star relative to the island of Montreal. NASA actually made this picture for me in a press release on a result we had. So this would be a bad idea to bring a neutron star to Montreal, but anyway, that's for scale. And so this is not matter like you're used to here on Earth. It's the density of this matter. You crush so much matter into such a tiny volume that if you went up to a neutron star and you took a teaspoonful, it would weigh 1 billion tons. So this is a different type of matter. The nature of this matter we don't fully understand, and that's part of the question that I'm trying to answer. They also are very highly magnetized, so the highest magnetic fields known in the universe. And they also rotate, as I showed you, and some of them rotate very, very rapidly. The typical pulsar rotates once per second. And you have to compare that. The Earth's rotation is once every 24 hours. The sun's rotation, you might not realize that the sun rotates once every 29 days. Pulsars rotate once a second, typically. But the fastest ones rotate hundreds of times per second. So the fastest one that we know of currently, although we're constantly searching for more of these, rotates 716 times per second, which you really have to stop and think about. And I've given this talk I don't know how many times, but each time I say that, I still get goosebumps because how can that be? But it is. We observe them all over the sky. We know about 2,500 of them in the galaxy. So you have 1.4 times the mass of the sun crushed into the size of a city, rotating like your kitchen blender. So just to give you a feeling for the speed. And by the way, I stay up late at night. I'm a night owl. And I once Googled to find out if I had to shamelessly plug my research group. The fastest known pulsar was discovered by my research group on supercomputers at McGill University. So we hold that record. Woo! Yes, McGill. And so I was curious, does it rotate faster? Really, does it rotate faster than the fastest blender on Earth? So I found the fastest blender on Earth, the Vitamix 5000. There it is. Apparently, it's really good for smoothies. And it maxes out at 625 rotations per second. So I'm very proud of that. And although I've also been told that laboratory centrifuges go over a kilohertz. So we haven't yet beat the biologists, but we're working on it. So to show you here's an example of a pulsar. This is a pulsar in a very famous nebula in the sky called the Crab Nebula. This is an optical image of the Crab Nebula. And if you take pictures of the central, so most of these stars are totally unrelated to the Crab Nebula, but the central star in the nebula is actually a pulsar. So if you take a very high-speed photography of this little box here, and so you take a really fast sequence of pictures. In fact, this entire sequence lasts 33 thousandths of a second, 33 milliseconds. You can see there's one boring, unrelated star that's always on, and then the other star is the pulsar that turns on. So time is going downward. Turns on, and then turns off, and turns on, and turns off. That is a pulsar pulsating 30 times every second. And so this is what I study. These are how I spend great portions of my day thinking about them. And the truth is, this is an optical image with an optical telescope, the kind you're imagining right now. But most pulsars do not like to produce optical light. Through quirks of nature we don't understand, they like to produce radio waves, which is another form of light. And so I don't use standard optical telescopes, I use radio telescopes. And these are the two largest radio telescopes in the world. This is a 100-meter aperture in Green Bank, West Virginia. And there it is for scale next to the Statue of Liberty and the Washington Monument, so you understand quite how large this object is. This is fully steerable, so you can steer it any way. And in fact, depending on what time it is, we actually have observations tonight. And we are using that telescope. I have a graduate student who is probably taking data right now. I hope he's taking data. Better be. The second telescope here is another telescope that I use a lot, is the 300-meter reflector in Arecibo, Puerto Rico. This is a different kind of telescope. It's stuck in the ground. It doesn't move. But these large objects that are suspended by these huge towers, 3 towers, those can move, and you can effectively point the telescope by moving these antennas. So it's antennas that basically radio waves come down, bounce off the dish, and then hit the antenna. And I'll just point out here, this is the visitor center. It's a 3-story building where there's a great science museum. If you're ever in Puerto Rico, I recommend coming. There's a snack bar and a little gift shop too, everything. And this thing here is a catwalk. That's a catwalk. So if you want to go stand up there, and sometimes you need to do this, and you could probably fit 100 people up there if you wanted, but you just walk up this catwalk over here. And here's a picture of me and a couple of friends standing. We're standing actually right next to this particular little tower. That's this thing here. If you zoom in, you'll see our knuckles are white. So I'm not going to pretend it's not scary up there. And I will just mention that if anybody's seen the motion picture GoldenEye, James Bond, GoldenEye starring Pierce Brosnan, there's a great scene where he's running on that catwalk. Or so it seems, because it's his stunt double. He was afraid to go on the catwalk. And so I'm very proud to say I have done things that James Bond was too afraid to do. Anyway, so this is what my data look like. This is data, so this is the intensity of radio light versus time. You see pulsations here. We call the time between pulses the pulse period. And these are real pulsar data taken with the Green Bank telescope. You can see the individual pulses here. This is actually a really bright pulsar. Most pulsars are nowhere near this bright. We're lucky when we get one like that. Because it's a radio telescope, how am I doing for time? Not a lot. Okay, little bit of time. I'll play this one thing for you. You know, it's radio waves. You can take the power output of your radio telescope, and we usually record it on digital computers and then analyze it, but you could also plug it into an amplifier and listen to it. And so I brought with me some pulsar sounds, where we've actually taken the output of the radio telescope and the electronics and plugged it into an amplifier, and I'm going to play for you some pulsar sounds. Okay, so this is a slow pulsar. Here, each one of those beats is that light flashing, and you're hearing a burst of radio emission. This one has a pulse period, that's the time between successive pulses. That was 7/100ths of a second. So boom, boom, boom. So each one of those is a rotation. The next one is a faster pulsar. It's in the constellation of Vela in the southern sky. And you're going to hear, it sounds like a little helicopter. Those are real single pulses. You can hear each rotation of the neutron star. And what you'll notice is you can hear cool things already. Not every pulse is the same amplitude. Sometimes a pulse is missing, but the next one comes back at the right time. In fact, that's a real feature, that if you record those times, as I can explain, these pulsars are superb clocks. Here's the pulsar in the center of the Crab Nebula. I told you 33 milliseconds. This is going to be irritating. So some of you can hear the individual pulses. Some of you, it might sound just like a sort of irritating tone, but now it's so fast, 33 milliseconds, that your ear and your brain have trouble separating the pulses. And the last one is one of the fastest pulsars. This is the second fastest pulsar known. This one has a period of 1.5 milliseconds, so 642 rotations per second. And now it's in the audio range, for real. So listen carefully. So you are hearing the pulses from the pulsar. Your brain now interprets it as a note. It's not actually exactly on the musical scale, but you could put it. So I don't know what that is. I can't tell you what note that is. But the point is, it's now a musical note, and this is what we don't actually listen to them. That's just for fun. But what we do with them is we time them. So some pulsars are really excellent clocks, in the sense that you can really set your watch by them. So that if you measure the period of some pulsars, not all of them, you can measure them with phenomenal precision. So the period in this case is, I'm not going to read out all these digits, but I'll just say that the uncertainty on this measurement is that range of error is 3 in the last digit. So this is one of the most precise numbers ever measured. And now, some pulsars are not so good. The error bar would be here. Some are even better than this one. But this is, it's truly astonishing precision. It has to do with the fact that you have this really massive, dense object rotating really fast. It's hard to stop it from rotating. It has huge, rotational inertia. And it turns out that some pulsars as clocks can be comparable to the world's best atomic time standards. And it's hard, so never mind, Rolex or clocks like that. The world's best atomic clocks are on par with not all pulsars, but some pulsars. And that is a very, very useful trait. It's useful to have a near perfect clock out at interstellar distances. Because you can do amazing experiments with the perfect clock when it's located across the galaxy. And in particular, when you find them, and we do occasionally find them in binary systems. So a binary star is when you have two stars that are orbiting each other. The sun is not a binary star. It doesn't have any companion, but most stars do. So if you look and you start to study it, most stars actually are binaries. That is, two stars orbiting each other. And now we're coming back to the Doppler shift. So that's really why I wanted to get a lot of talk about the Doppler shift a lot, because the pulse period, tick, 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 is like a little clock. And the way we know that pulsars are in binary systems is because of the Doppler shift. When the pulsar is moving towards you, it ticks a little bit faster. It's blue shifted. When the pulsar is moving away from you, it ticks a little bit slower. It's red shifted. So as the pulsar moves away and towards you in its orbit around another object, the pulse period makes a sine wave. So this is now, I'm plotting here, pulse period as a function of time. Each of these is a data point, and it's a huge effect. We measure these pulse periods and we see, and most of them just are flat. This one is obviously a binary. It's going up and down, up and down. Sure enough, you can go and take another telescope and sometimes you see another star. That's also, you can see that it's moving. So this is what we do. It is so cool. When you find one of these in a binary system, you can study the binary motion with exquisite precision because these clocks are so amazing. And you can just see this precision. The error bars are on the points. There's no ambiguity. You can measure and you can even see, oh, the points are not quite on the line. My student made a mistake. Go back, fix your fit. It's not perfect. Let's skip that. The first binary pulsar discovered was in 1974 by these two gentlemen, Russell Hulse, Joe Taylor. It's a pulsar in orbit around another neutron star. This man, Joe Taylor, was my PhD thesis advisor. One of the nicest people. When people ask me who my greatest mentor was, it was him. Really wonderful guy. And they found the first binary pulsar. And what was amazing about it is that the two pulsars orbited each other every 8 hours. So you know the Earth goes around the sun every year, 365 days. And that's fine. You can observe its orbit. It's always going around. It's perfect. Here you have two objects orbiting each other every 8 hours, so 3 times a day. That motion now, we call that motion relativistic because the speed, the orbital speed, is a significant fraction of the speed of light. And here we come back to Einstein. For orbits like the Earth around the sun, once a year, the motion is so slow that you could use old-fashioned, this is Isaac Newton here, in case you don't know. This is Isaac Newton, and for those of you who took Physics 101, you probably remember this formula, you probably hated it, but there's Isaac Newton. This formula will work to explain the motion of orbits as forces, mass times acceleration. Never mind, the point is it's simple. And once you start something orbiting, it will orbit forever according to Isaac Newton's laws. Then Einstein came along, and it was a little bit more complicated. He discovered, if you want, the laws of general relativity and showed that actually, if you have two objects orbiting each other, they will one day coalesce. It may take billions of years, but they will, because in this picture here's the Hulse-Taylor pulsar. Here's one pulsar orbiting some other star, and this green grid is supposed to be an imaginary grid where you see what Einstein predicted, which is what we call gravitational waves, that is, ripples in space-time. So according to general relativity, two objects orbiting each other lose energy and make actual ripples in space-time that go out and it's hard to measure them, but because they're producing, it takes energy to make these ripples in space-time, eventually those objects will coalesce. And so Hulse and Taylor here, they found the first binary pulsar, and the reason they're laughing is because they asked the question, was Einstein right? When you have two objects orbiting each other every 8 hours, you can test, because those objects should be producing huge amounts of gravitational waves and should be coalescing. And this is the plot that won them the Nobel Prize in 1993. It doesn't matter exactly what's on this axis. This is year. They studied this for many, many years. And what they showed is that orbit is slowly decaying exactly as Einstein predicted. So if Newton was right and Newtonian mechanics applied, all those data points would lie on this horizontal line here. Instead, each of these is a data point with an error bar. You can see, and this is the calculated prediction from general relativity, and you can see those data points lie exactly on the line. And there's Joe with his 1993 Nobel Prize. And I'll just tell you one personal anecdote is he won the Nobel Prize. The Nobel Prize was announced the day before I was due to defend my PhD thesis. And we were at Princeton University, and when he announced the Nobel Prize, and they pulled out, I don't know where they got it so quickly, but tons of champagne and all this stuff, and there was a big party, and in the middle of the party, he went to the bar, and he grabbed a bottle of champagne, and he came over to me, and he said, "I'm saving this for you tomorrow, Vicky." And I thought, isn't that nice? Isn't that touching? He didn't have to do that, but he was a really, really nice guy. And so the question, was Einstein right? We don't believe in rock stars in science. We test theories, and he was wrong before. He wasn't wrong with the Hulse-Taylor pulsar, but there's a whole range of physics where 8 hours is great, but there is much more relativistic objects in the universe that have never been tested. Einstein's theory has not yet been put to the test. And in fact, these gravitational waves that we infer to exist have never actually been detected directly. And so what's new, Seymour? What's new? Part of my research program is to use pulsars to test Einstein's theory. We believe the universe is pervaded by these gravitational waves everywhere, and because we have all these near-perfect clocks, we're watching them, monitoring them, typically once every few weeks, using the world's largest radio telescopes to look for signs of these gravitational waves that would basically cause the clocks to look a little bit off. Because the distance is a little bit larger, the pulses take a little bit more time to come to you. The idea is that by combining data from many of these pulsars, we're hoping to detect Einstein's gravitational waves. And we haven't yet done it. This is a large collaboration, 60 people, 4 different continents. If you want to read more, you can check out these links. The North American Nanohertz Observatory for Gravitational Waves, that's NanoGrav, that's my collaboration. That we're hoping that we're going to detect gravitational waves, hopefully in the next 5 to 10 years is our best estimate. And one way to do this, to make this experiment more robust, is to find more pulsars. And so that's what one of my big research projects is today. I'm constantly searching for pulsars using Arecibo. Data from Arecibo are taken typically every few weeks, sent to a supercomputer that's located downtown. It's operated by Compute Canada and by McGill University, and we are analyzing that, and here's a picture of some of our latest discoveries. We've discovered pulsars every week. This is a top-down view of the Milky Way galaxy. These are all, each dot is a known pulsar. All the blue ones are ones that our survey has discovered, and this is really all thanks to my wonderful research group, and there they all are, Paul, Eric, Ingrid, Wendy, Rob, Pragya, Alex, Rob, 2 Robs, and Emily and Chitrang. These are wonderful students who do a huge amount of work. This pulsar searching today using supercomputers, pulsar studies tomorrow, I just want to mention, you might not be aware, but the Canada Foundation for Innovation has given money for us to build a huge radio telescope right here in Canada. It's going to be called the CHIME Radio Telescope. It's actually under construction, and in fact, it's doing really well. This is the CHIME Radio Telescope. You can't quite tell how big it is. In traditional Canadian units, we measure it in hockey rinks. It has the area of 6 hockey rinks. And in fact, if you look at this, it doesn't look like a normal radio telescope. It's actually quite a clever design. It doesn't move, no moving parts, so we could build it really cheaply. We just wait for the sky to rotate overhead every day, and we hang 1,024 radio receivers and combine them all using a supercomputer located on the site. Just to set the scale here, you see this axis is where we're going to hang all those radio receivers, and there's a picture of the CHIME collaboration, 50 people standing in one of those axes. So just to get a feeling for the scale here, it's very, very large, very exciting project, and it's what I'm spending a huge fraction of my time right now on. So with that, I want to thank you for your time and your attention. Thank you for coming. Thank you for listening. Thank you for laughing at my jokes. But I'm going to say one last thing. And this